We've made it to the final stretch, the final topic for the rest of the semester, and that is a group of minerals called the silicates. And today I'm going to introduce to you the whole family of the silicates, and that introduction in the textbook is on pages 434 to 438. And we're going to spend the rest of our semester talking about silicates, because when we look at pictures of the Earth, pictures of our other rocky planets, basically every single mineral that we're seeing that comprises 90% of terrestrial crust or planetary crusts is composed of silicate minerals. They're the dominant minerals inside of, well, maybe not dominant, but very important minerals inside of the mantle and also soils and building materials. And so here, just to start it off, I want to just make a point, and it's probably obvious, is that these are dominant minerals, the building blocks of rocks. And we can say that these are dominant in the crust. 90% actually of the crust is made up of these minerals. The only other 10%, that's basically calcite and limestone. It's making up a big part of the mantle. Think olivine and peridotite, and soils from where we get all of our food to sustain life, and our building materials like bricks and concrete and glass. They're all being derived from silicate minerals in large part. So maybe that's obvious, but it's important to start our notes maybe with some obvious things. We also could say, just to give some stats, that ends up being well over 1,000 minerals are silicate minerals. This is a fifth of all of the minerals that we have identified yet, and it's about 40% of all the common minerals that we would deem kind of normal. And so we can think of it this way with this pie chart, which I snagged from the textbook, and basically gives you the names of, and so this is 90% of crust. And how does this break down? Well, plagioclase is a huge component, and when I think plagioclase, these are the rock types or the minerals appearances that I'm going to expect. Things like anorthite plagioclase and albite plagioclase can have different colors. Then alkali feldspar, another name for that is potassium feldspar. It tends to be the pink color that we see in granites. We all know what quartz is like, and you might have actually guessed that quartz played a bigger role. It plays a bigger role at the veneer, the sedimentary veneer of the crust, but not deeper in the crust where plagioclase dominates. So here's quartz, our muscovite and our biotite micas are here, 5%. Amphiboles, these are things like hornblende. This is a picture of, what is this, a picture of pyroxene, I think. That would be in this other silicates. And this is olivine also probably fitting into this. Oh, there's pyroxene, I missed it. Okay, so this is kind of our breakdown and just a quick graphic representation of silicates. But that's not where we spend the bulk of today's lecture. Instead, what we need to do is get into the shared structural elements of all these different silicates and then unpack where the differences come in. So the basic shared structure of the silicate family is the SiO4 4- tetrahedron. And we're going to be drawing tons of tetrahedrons today, so get your pencils ready, get maybe some colors ready. Maybe one color can be silica, another color can be oxygen, and I'm going to do my best to draw really good triangles as we draw these tetrahedrons today. But you know, it gets a little sloppy sometimes on this writing pad. So how do we get to that structure? Well, we get there with the concept of coordination number, which you learned about earlier this semester in the crystallography part of the class. And remember, coordination number is the ionic radius of the cation divided by the ionic radius of the anion. And so here our cation is silica 4+, and the radius of that is 0.4 angstroms. And oxygen 2- is our anion, and that has a ionic radius of 1.4. So we set up our math and we do 0.4 divided by 1.4, giving us a value of 0.286. Now, what does that number mean? Well, remember, there were some cutoffs when we get to structure, and the upper cutoff is with the linear, or not linear, it's triangular structure, and that's 0.2. 225. And there's a bottom cutoff that goes towards octahedral arrangement, and that is like 0.414, something like that. And in between the two is our tetrahedral structure. And so you can see that 0.286 fits really nicely in that framework. And so to visualize this structure, we're going to try to draw the silicate tetrahedron. And you can do this in a variety of different ways. Eventually, we're just going to get to a point where we're drawing triangles like this, where we are going to put our oxygens at our corners of our triangle, and there's going to be one back here. And then in the center, there's going to be this oxygen. But before we get to that like kind of more shorthand drawing, let's do it a little bigger and cleaner first. And so to start, we're going to put silica, and it's going to be hanging out here in the middle. And away from that silica, there is going to be oxygens. And the oxygens have these bonds. So here's a bond to an oxygen. And here's a bond to an oxygen. And going up, there's another bond to an oxygen. And then going straight behind the silica into the page, there's going to be another one right there. And so if we were to kind of draw this out, we could connect it and make a triangle. I'm doing a dash line triangle, but you don't have to do it. This is just kind of visualization. And so the way this works, what we end up having is we got, how do we go? Oxygen 2 minus, oxygen 2 minus, oxygen 2 minus, and then another oxygen 2 minus back here, right? Good. And how do these bond with one another? This is a silica 4 plus. And what ends up happening is that one of the 4 pluses goes up to this 1 negative, leaving us hanging out here, free to bond with other things, is another free minus, or I guess electron. And so the silica shares a positive in this direction, and then into the back in that direction. The oxygen here shares a negative, and towards the back of the page it shares a negative. So each one of these oxygens has one kind of free negative where it can bond outwards. Okay, and what we call these oxygens at the ends of the tetrahedrons that aren't bonded and have a negative, these are called bridging oxygens. And what they are is they are available to bond. And so I guess we could define it. Let's just define this as these are oxygens that are available to bond. At least in one direction, right? And only in one direction, because the other direction is they're bonded towards that silicon 4 plus that's hanging out in the middle. And so how could you visualize bridging oxygens at work? Well, let's say we have a silica tetrahedron right here. All right, so here's our drawing of our silica tetrahedron with oxygen, and oxygen, and oxygen, another oxygen in the back, and they're forming this nice tetrahedral shape. And there's a silica right here in the middle. Well, this bridging oxygen might bridge into another tetrahedra right here. Okay, and then there we go. There's our structure that we've drawn. And this one now is sitting there available to bond. And so we could put in another silica tetrahedron. And you can see that this is just one of the possible arrangements, and you could probably with your crystallography skills, you could puzzle through other ways to pack triangles, these tetrahedrons, around one another to create different shapes and structures. And that ends up what nature does, and how we at least try to explain nature's packing with these different silicate subdivisions. So this is where we're going to spend basically the remainder of this lecture. Depending on how fast the drawings go, that's going to depend on how long the rest of this lecture goes. So we have silicate subdivisions. Each division is based upon the silica tetrahedron, and importantly, the number of bridging oxygens. You could also think of this as in terms of polymerization. The more bridging oxygens you have, the longer polymer chains you have of silicate. So the first type, there ends up being 6 of these. The first type is called, the family is called the Tectosilicates. And the Tectosilicates are the simplest of them all. Neso, I think, is affiliated with the word island, I think in Greek. And so what they have is there's just a single SiO4 4- tetrahedron available to bond with other cations. And so if we were to draw this, and we're going to draw every single one, here's what this one will look like. We just get a single tetrahedron. We go, let's see, oxygen, 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 oxygen. I'm going to dash these lines here in the back so we can kind of get some three-dimensionality. And sitting here in the middle is our silica. All right, that's the framework that I want you to picture. And then each of these non-bridging oxygens might be able to bond to something like calcium or magnesium. And in fact, that's what it does. And minerals like olivine or garnet. These are kind of famous nesosilicates. Oh, zircon is another nesosilicate. Now, that's all we're going to talk about nesosilicates for today. Sorosilicates is our next little subdivision to talk about. And when I see soro, I'm in a university, I think of sorority and like sisters. And so that's what's going on here, is that there's two of them end up being bonded together. Sorority, I don't know how to spell that. Sorority sister is what I think about when I think of this. And so what we have is two tetrahedron bonded together. Two tetrahedron bonded over one shared bridging oxygen, and it combines to form a base unit of Si2O7 6-. To draw this, we need to put two triangles touching at the corners. So we're going to do one triangle pointing down. I keep saying triangle interchangeably with tetrahedron because I'm drawing triangles, even though my mind is visualizing 3 dimensions, tetrahedron. Okay, so let's see. We're glitching out a little bit. There we go. There's our upper triangle. We can make these look prettier. Putting in the oxygens, kind of dashing in the shape to give us some 3-dimensionality. We can't forget our silicons, which I guess I'm going to do blue for the rest of this lecture. That is the structure of the sorosilicates. Our example here, there's many fewer sorosilicates. Epidote is probably the most famous mineral that has this structure, and it has a gem associated with it called tanzanite. So those are our sorosilicates. Next up on the list are the cyclosilicates. Cyclo has to do with the word circle, and so the drawings now start to get more complicated. But I'll try to teach you how to draw these in a nice way. So cyclosilicates, let's make sure you spell that right. These are circles. And so another way to think about it is a closed ring of SiO4 tetrahedron bonded together. It's a closed ring of 6 tetrahedrons. And they combine to form a base unit of Si6O18 12-. Our examples are beryl and tourmaline. Those are our best examples. Beryl, that's not how you spell that. There you go. And tourmaline. And this one's probably the hardest to draw of all of them. The phyllosilicates are pretty tricky too. So what I want you to do is start with like a real light hexagon, but make it a really nice clean hexagon. And these faces of the hexagon end up being the bases of each triangle. Okay, so there's our hexagon that we start with. And then what we're going to do is put in our 6 tetrahedron off of this. So this upper one, there's our triangle. And then we're going to do another triangle, another triangle. Right, you see what we're doing? Every single one of the faces of the hexagon is the base of a triangle. Hopefully your triangles are sharp and equilateral, because they're not really triangles, right? They're tetrahedrons. We're going to put in our oxygens. Notice how many are being shared, right? There's so many being shared to form this ring structure. We could put another one here. We're making that 3-dimensionality. Da, 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 da. And then we can put in our silicas. I keep saying silica, I mean silicon. Silica is SiO2, which is quartz. I'm using that incorrectly. The next family are called the inosilicates. And ino has to do with chains. And so what you're going to picture with inosilicates is infinite chains of SiO4 tetrahedron. And our examples of the inosilicates are actually going to be pyroxene and amphibole, which are very important. But we break down this, sometimes people joke about it, they call it the chain gang. And the chain gang of the inosilicates can have chains that are single chains, and you can also have a group of double chains. And they end up having slightly different structure. So we're going to draw each of them. The single chain of the inosilicates ends up being Si2O6 4-. And the double chain has a base unit of Si4O11 6-. Okay, and now to draw these chains, what you're going to do is draw a straight line that's very light. And then coming from this straight line that's very light, we're going to do triangles that point down, bonded to a triangle that points up. Okay, and we can do this infinitely. You get the idea? Okay, we can just keep going on. And each one is our tetrahedron. And that's how we create the single inosilicate. Put our silicons in there too. And our double chain is just a little more complicated. What we're going to do is we need now two straight lines directly parallel to one another. And our triangles that come off of them touch. So we're going to start touching more now. So there is one triangle, and its apex is touching this triangle. And then we do another triangle, pointing down. This one points up. Okay, and we repeat. So now we come down again, and then we go up again. See, so this one goes through. There we go. All right, you see the pattern we got going here? That can now infinitely repeat, moving in this direction, or of course this direction. We can make sure you finish off your drawing. You can always pause the video if I'm going a little too fast. Let's put in our silicons. That is our structural framework. And we're going to draw just one more. It's called the phyllosilicates. There's actually one more even after that, but it's so hard to draw, I can't do it. So I'm just going to show you a picture. So this is our last drawing. This is a family called the phyllosilicates. And the phyllosilicates are the sheet silicates. So these are our micas, the things that are going to peel apart really easily. These are sheet silicates, and it has a framework of Si2O5 2-. And our example is the micas. And this drawing is our hardest one to do. So to start, hexagons. We're going to take a light hexagon, as balanced and nicely drawn a hexagon as you can possibly do. And then we're going to let one corner of that hexagon touch or be used to set up the next hexagon. So what I'm going to do is I'm going to use this corner right here as the starting point for the next hexagon. Okay, you can see where a triangle maybe start to be forming. And then I'm going to put in another hexagon right here. And it's these hexagons, it's kind of like ring shapes, they're going to be the basis for all of our tetrahedrons. And so now, once you get something drawn like this, and we can infinitely repeat it in a sheet as much as we want, we can start putting in our tetrahedrons. So there is one. And here is another. And from each one of these, just like we did with the cyclosilicates, we can start putting in all of our tetrahedron. All right, so either pause the video and do it yourself, or just kind of bear with me as I'm drawing all of these in. What else do we need to do? Well, we got to do it for this hexagon. So there we go. Oh, that one got a little big. Oh boy, I'm getting sloppy. That's because my hand's cramping. You're getting the idea though, right? We're sharing our edges, and this is presenting this really big sheet of SiO4 that's all bonded together along bridging oxygens. Okay, I've almost gotten this done. We're putting in the three-dimensionality to them all. You can, I forgot to do that on the previous pictures. Right, you can do those little dot lines and then put the silicon in the center of each of our tetrahedrons. And that is our structure of the phyllosilicates. Now, Professor, you haven't talked about quartz and plagioclase yet. The feldspars. Well, that's right, because, dear students, family F is the Tectosilicates. And the Tectosilicates are the major rock-forming kind of crustal minerals. This includes our quartzes, and all of our feldspars. And tectosilicates are considered to be builder. Like tecto means build, so we're going to consider this the builder or the framework silicates. And I used to work in construction, so a framework to a house is like all the wood that builds up in 3 dimensions, and that's what's going on here with the tectosilicates, and it makes it really hard to draw. Every corner ends up being shared, and the tetrahedron are all arranged in 3 dimensions, and so I can't draw it, so I'm going in here to a textbook that I like, and you can see all these different drawings that we've already done. Oops, let me get that centered back up again. Okay, good. So here's our nesosilicates and our inosilicate single chain, our double chain inosilicates, our phyllosilicates, and then right here, this is what I'm talking about for the tectosilicates. Maybe you can draw that, but maybe you can't, and all you can do is just pause this video and look at it with concerned eyes for a minute or two, and you can see how all these tetrahedron arranged are kind of rotated around as they build this 3-dimensional network. So those are our different silicate tetrahedron structures, and as we finish, I just want to do real quick, what about all the other cations? So we're going to call this other cations, and how these other cations are bonded into silicates. And the way this works out is it's all controlled by coordination number. And this is table 18.1 from your textbook. And if you want to snag it or write some of this down, you can. But I guess the point I just want to make somewhat quickly is that each of these cations right here have different charges. And with their charges and with their different ionic radii, they're going to have different coordination number. And so the point about the other cations is that they have structure. All right, so we're going to say their structural arrangement is controlled by coordination number. And there's 2 main groups I want to bring in here. One is it's just aluminum, because aluminum 3+ substitutes into silicate structure very, very often. And when aluminum 3+ is in a silicate mineral, it can either have a tetrahedral arrangement or it can be octahedral. And all the other cations, essentially, well, not potassium, not sodium and calcium, but look at all these right here. All of these cations end up having octahedral arrangement. And so we're going to say here that octahedral arrangement or coordination for most other cations. Let's write them all down. This is, when I talk about this, this is manganese, magnesium. I'm glitching out just a second, bear with me. So magnesium, this is our irons, titanium. These elements, actually even sometimes calcium, will have an octahedral arrangement in our silicate minerals. And that means if we were to draw it, and we've drawn octahedrons a number of times this semester, we're going to have this appearance. I'm going to try to draw it in 3D. There's our octahedron, and at each of the corners, there's 6 corners. Those 6 corners are each oxygen 2 minus, oxygen 2 minus, and then sitting here in the middle is going to be our cation. Magnesium, iron, etc. So when we get towards building mineral blocks, we talk a lot of times about T and O. And when we're talking about mineral structure, T stands for tetrahedral and O stands for octahedral, as just quick shorthands to try to, instead of having to draw all these triangles again and again like we did today.